Something strange has happened in the universe, and Brian Cox has warned that the implications are too massive to ignore. The universe, as we know it, began in an incredibly hot and dense state, a singularity that expanded and cooled rapidly, giving rise to the entirety of space, time, matter, and energy. But the ultimate destiny of the universe's continuing expansion remains an unresolved scientific mystery. Scientists are racing against the clock to unravel this mystery, combining innovative mathematical models with experimental data. Despite their progress, the universe continues to defy our understanding, revealing itself to be increasingly complex and strange. And now, the renowned scientist Brian Cox has just issued a warning about a groundbreaking discovery of something strange that's happened in the universe. Let's dive in and unpack this together.
One level, it's a tour of the universe in all its terrifying vastness. People tend to get frightened. You can't visualize it. It seems overwhelmingly massive, and we seem overwhelmingly small. To be a finite speck in an infinite and potentially eternal universe. But the most shocking revelation is in the sequence about black holes. We have found, through considering and exploring the physics of black holes, that we might all be holograms. Think about the fact that although we are tiny and small and fragile, we might be tremendously valuable.
Our universe, which was once an infinitesimal speck, no greater than an atom, is now a vast expanse stretching billions upon billions of light years across. Yet existing in it is something unique, possibly the most precious planet in the universe, planet Earth. A blue marble floating in the void of space, the only known location in the universe that sustains life. It is the birthplace of humanity and the reference point of our observation of the cosmos. Concealed within the depths of this cosmos are some of the most enigmatic secrets the universe has withheld from us. The solution to these secrets may have the potential to revolutionize our understanding of the cosmos and expand the boundaries of human knowledge. Astronomers today have captured pictures of stars, galaxies, their collisions, and the nebula clouds to comprehend all that is possible.
Again, we didn't know of any planets beyond our solar system because we hadn't detected them. So even if we thought, well, we can't be special, we didn't know. And then in the early 1990s, we started being able to detect planets. And now we've detected well over 3,000. We've got missions up there like the Kepler telescope that are just trying to detect planets. So thousands of them. So now the statement is that pretty much every star in the sky will have planets around it, which is remarkable. If you go out, it's a clear night, you go out and look at stars, you can imagine that there will be solar systems around every one. So that allows us to start thinking how many potentially Earth-like planets might there be in the Milky Way galaxy? And the answer is about 20 billion. What you mean there is a rocky planet, the right distance from its star, possibly, if everything's right, to have liquid water on the surface and so on. In a nice distance from the star, perhaps 1 in 10 stars. We talk about a thing called the habitable zone. Now, in the solar system, there are 3 planets in the habitable zone. There's Venus, Mars, and Earth. Venus is close to the sun, Mars further away. All of those planets, though, we think had water on the surface. So they all could have been habitable in that sense. And still, we're looking for life on Mars to this day.
The Hubble Space Telescope, with over 1 million images captured, has been a pioneer in our exploration of the cosmos. The Kepler Space Observatory has discovered over 4,000 exoplanets, some of which are believed to be similar to Earth and capable of sustaining life. But as scientists delve deeper into the mysteries of the universe, they're beginning to realize that the truth is far more complex and stranger than they ever imagined. Now, renowned scientist and science educator Brian Cox have recently made a startling revelation of something strange that's happened beyond the edge of the observable universe. But before we dive into this fascinating revelation, let's provide some important context. Everybody knows that gazing at distant celestial bodies is essentially looking back in time. When you look up at the night sky, you're not actually seeing that star as it exists right now. Rather, you're witnessing the light it emitted many years ago. For all we know, the star could have gone supernova over a century ago, and it may be centuries more before we learn of its demise. The frequent news reports of newly discovered distant stars billions of light years away have contributed to a common misconception: the belief that many of the stars in the night sky may have already perished, unbeknownst to us. The notion is sometimes even propagated in educational settings, but it's not the most likely state of affairs. While it's technically possible, it's exceedingly improbable. When people discuss the night sky, they're typically referring to the approximately 9,000 stars visible to the naked eye from Earth. Although we're observing those stars as they existed in the past, the time-lapse is relatively short on a cosmic scale. The stars we see in the night sky are generally the closest to our planet, contained within our own galaxy. On average, these stars are only about 1,000 light-years away, with the most distant visible star being roughly 16,000 light-years away, but that outlier is barely discernible. Even considering the average star, 1,000 years sounds like a long time. How can we be so confident that all of those stars are still thriving in their respective corners of the galaxy? The lifespan of stars typically ranges from 50 million to 20 billion years, with the most massive blue supergiants living for only around 10 million years, though those are exceptionally rare. If we assume an extremely conservative 50 million year lifespan for every star in the night sky, the time it takes for their light to reach Earth is only a minuscule fraction of their total existence, around 0.002%. This translates to a mere 18% probability that even one of the 9,000 visible stars has already perished. Of course, this line of reasoning applies only to the stars visible to the naked eye in the night sky. When we consider all the stars observed by powerful telescopes, many of those have indeed reached the end of their life cycles. This is likely the source of the confusion, leading to the commonly held belief about the night sky. But for the stars we can see with our own eyes, the chances of any of them having died off are extremely low. We'll come back to this in a moment. Now, to fully grasp the significance of Brian Cox's recent revelation, we must first address a common misconception. This misconception arises largely from imprecise explanations provided by literature and science communicators. The universe is believed to encompass everything, excluding any potential multiverse. Thus, the assumption whenever one discusses the universe is that it refers to the entirety of the cosmic domain. However, there are actually different ways we can define the universe. These include the observable universe, the causal universe, and the entire universe. Most information learned about the universe pertains to the observable universe, though a distinction is rarely articulated. The observable universe, as the name suggests, is the part of the universe that we can directly observe. This extends 46.1 billion light-years from Earth in all directions, but the term is somewhat misleading. Consider the example of galaxy Glass Z12, the farthest galaxy currently observed, located approximately 33 billion light-years away from Earth. Yet, due to the accelerating expansion of the universe, light emitted from that galaxy today will never reach our planet. We can only observe the light it emitted 13.6 billion years ago, which has finally reached us. Thus, it's considered part of the observable universe, even though its current location lies beyond our view. Beyond the observable universe is the causal universe, the region of spacetime that could theoretically have a causal relationship with us on Earth, as photons from that distance could potentially reach our planet. This can be thought of as the upper bound of the observable universe. As technology advances and telescopes become more powerful, the observable universe expands. It's believed that future technological breakthroughs will allow us to see even further, yet the causal universe represents the maximum extent the observable universe can ever reach, no matter how much our capabilities improve. However, beyond both the observable and causal universes lies the entire universe, which we assume exists even though we cannot directly confirm it. All of our best cosmological models suggest that the universe extends well beyond what we can observe, likely to infinity. As such, it's presumed that our infinite universe has no actual center, even though visualizations often depict Earth at the center of the observable universe. This is one of the major differences that distinguish the observable universe from the entire cosmic domain, a distinction that's often misunderstood or poorly communicated. Of course, one could argue that this assumption about the lack of a cosmic center is itself another misconception. After all the observable scientific data indicates that Earth is indeed the center of the universe we can see. This view is based on the fact that we can observe the same distance in all directions, and the sphere around Earth comprises the observable universe. The shift from geocentric to heliocentric models of the solar system led scientists to adopt the default stance that Earth is an average, unremarkable planet. This perspective remains the default for scientists, and for good reason. However, there's no actual evidence that this assumption is true. It's simply an inference based on sound logic and extrapolation. Similarly, the assumption that the entire universe is either infinite or a massive closed shape, with Earth not located in any special position within it, is also based on logical reasoning rather than direct observation. While these assumptions are likely accurate, the currently available physical evidence does not conclusively rule out the possibility that Earth is, in fact, the true center of the universe. Our knowledge of the cosmos has expanded substantially over the previous century. However, every answer uncovered appears to spawn countless novel questions that we have no idea how to address. Brian Cox explains that we have a tool called the Sloan Digital Sky Survey, which maps the positions of galaxies across the sky. This allows us to determine how much of the sky has been surveyed and how many galaxies have been counted. By extrapolating this data across the wider universe, we can get a picture of a vast and possibly infinite universe. Cox notes that while we know the universe is much larger than the portion we can directly observe, whether it is truly infinite is another question. We can measure the age of the universe by tracing the expansion of galaxies back in time, and this indicates the universe began around 13.8 billion years ago. However, Cox clarifies that what we really know is that the universe was in a very hot and dense state at the time, rather than the universe having an absolute beginning. There are even theories that the universe may have existed in some form before that, suggesting the possibility of an eternal universe. Some people find the idea of an eternal universe more unsettling than the notion of a universe with a defined beginning. The universe is vast, but it's only with recent advancements that we can comprehend how unimaginably immense the universe, or even multiple universes, may actually be. Eternal chaotic inflation, which generates multiple universes, builds upon the theory of cosmic inflation. Although inflation is generally eternal into the future, it's not eternal into the past. Alan Guth detailed this in a paper published in 2007, noting that new inflation does not produce a perfectly symmetric universe due to quantum fluctuations during inflation. These fluctuations may cause the energy and matter density to be different at various points in space. Quantum fluctuations in the hypothetical inflation field produce changes in the rate of expansion that are responsible for eternal inflation. Those regions with a higher rate of inflation expand faster and dominate the universe, despite the natural tendency of inflation to end in other regions. This allows inflation to continue indefinitely. Modern physics has dramatically transformed our understanding of the cosmic cosmos, offering not only glimpses of the universe's potential future, but also providing insights into the overall shape of the universe itself. Brian Cox explains that from the theory of inflation, the best way to explain the observable properties of the universe is that it's vastly larger than the portion we can directly observe. For example, we've measured the geometry of space to be flat, like a tabletop, rather than curved like a sphere or saddle. According to Einstein's theory of general relativity, the curvature of space is determined by the matter and energy content within it. What we find is that there's precisely the right amount of stuff in the observable universe to result in a completely flat geometry. The most favored explanation for this unusual flatness is that the universe is much bigger than the region we can see. The theory of cosmic inflation suggests the universe expanded exponentially in the earliest moments after the Big Bang, creating a vast expanse far beyond our observable horizon. This indicates the observable universe is merely a small fraction of the full cosmic expanse, which may extend infinitely. The flatness we measure is thus a consequence of this larger-than-observable universe, rather than being a fundamental property of the cosmos as a whole. Because we cannot detect space beyond the edge of the observable universe, it remains unknown whether the total size of the universe is finite or infinite. Estimates suggest that the entire universe, if finite, must be over 250 times larger than the observable universe. Astronomers calculate the age of the universe by assuming the lambda CDM model, accurately describing the evolution of the universe from a very uniform, hot, and dense primordial state to its present state, and by measuring the cosmological parameters that constitute the model over time. The universe and its contents have evolved. For example, the relative population of quasars and galaxies has changed, and space itself has expanded due to this expansion. Scientists on Earth can observe the light from a galaxy 30 billion light-years away, even though that light has traveled for only 13 billion years. The energy from the Big Bang drove the universe's early expansion, and since then gravity and dark energy have engaged in a cosmic tug-of-war, with gravity pulling galaxies closer together and dark energy pushing them apart. Whether the universe is expanding or contracting depends on which force dominates, gravity or dark energy. Besides dark energy, there's also a mysterious, invisible substance that fills the universe which no one's ever directly observed. This hypothetical form of matter, thought to account for approximately 85% of the matter in the universe, is also known as dark matter, but we have yet to fully understand its nature. We may never have a definitive answer to the question of whether the universe is infinite or has an actual boundary. However, what we do know is that the observable universe is stupendously large in volume. This vast expanse of space is estimated to contain anywhere from 200 billion to a trillion galaxies, according to varying estimates, and each galaxy has an average of about 100 billion stars. These gargantuan numbers are both mind-boggling and awe-inspiring when we look into the night sky and try to comprehend the unimaginable scale of the universe. What's the deal with dark matters and aliens? Hopefully this doesn't surprise you, but the cosmos is composed of matter. The three subatomic particles most individuals learn about are negatively charged electrons, positively charged protons, and neutral neutrons. However, those are only the subatomic particles of matter. There are also antimatter particles, positrons, antiprotons, and antineutrons. These three particles are identical to their matter counterparts, except they have the opposite charge. Additionally, there are some other characteristics that are reversed as well, but the charge is a significant one. When matter and antimatter come into contact with one another, they're instantly destroyed and transformed into energy. Given the volatile nature of matter and antimatter, they obviously cannot coexist, so it makes sense that the universe would be made up entirely of matter, right? Well, actually, it doesn't make any sense that the universe exists at all. According to the Big Bang Theory, an equal amount of both matter and antimatter would have been created, and as these particles came into contact with one another, they would have been destroyed and turned into energy, meaning no stars, no planets, no nothing. Now, obviously, that didn't happen, and here we all are, but the question is, why? Why wasn't all matter and antimatter destroyed, and why did matter prevail? Well, according to the Standard Model, the prevailing theory in particle physics, there's no reason anything should exist, which means our understanding of physics is just nowhere near complete. Until the 1960s, it was believed that matter and antimatter were symmetrical in every way, with a negative charge in the matter being a positive charge in the antimatter equivalent. But the absolute values of all things pertaining to these particles were always thought to be identical. However, in 1964, researchers discovered a tiny discrepancy in the way that K ions and anti-K ions decayed, and some other discrepancies have been found as well. But we cannot emphasize enough just how minute these variations are. Nothing's been discovered in these discrepancies that would violate the standard model, and certainly not to the extent it would provide an explanation for why the universe is comprised solely of matter. There are some proposed modifications to the standard model that hope to fill in some of the gaps in our understanding, like the most prominent proposal, supersymmetry. With any luck, the new and improved Large Hadron Collider can help fill some of the holes in our knowledge of certain atomic particles. According to scientific folklore, Enrico Fermi, the creator of the first nuclear reactor, was discussing UFO reports with his fellow physicists while strolling to lunch. They were all unsurprisingly cynical, believing that none of the reports of UFOs were genuine. However, Fermi suddenly exclaimed, "Where is everybody?" which the others immediately understood to mean extraterrestrial beings.
The flip side of this is there are loads of planets out there, and there's been loads of time. This has got a name, actually. It's called the Fermi paradox, after someone called Enrico Fermi, a great Italian physicist, who asked this very simple question, which is, where are they? Because given the number of planets, given the number of stars, and given the amount of time in this galaxy for complex life to emerge, it seems as if at least a few civilizations should have become a spacefaring civilization. So part of the evidence, part of the great conundrum here is that, so on the one side, yes, we've got the history of life on Earth, which says that we took a long time to emerge. And so it looked quite like an unlikely process. On the other side, you've got all this real estate. And you have this, so if you think about where we could go, what could we become as a civilization? So already we are becoming a spacefaring civilization now very quickly. So give us 1,000 years. We don't destroy ourselves or do anything stupid. I'm sure we're going to be on Mars, we're going to be on the moon, we're going to be thinking perhaps taking our first steps out to the stars. Give us 1,000,000 years, 1 million from now. If we survive, we should become a spacefaring civilization. Now, 1 million years, the galaxy has been around for the age of the universe, 12, 13 billion years. So it only takes a few civilizations to have evolved a bit ahead of us. 1 million years. Well, let's say 1 billion years. 1 billion years, it's still nothing. You get some civilizations that evolved 1 billion years before us. Why can't we see them? So then people start saying, well, maybe there's a finite life that all civilizations have. Maybe they destroy themselves. Maybe they don't become spacefaring civilization.
The paradox stems from the lack of evidence of any extraterrestrial existence, in contrast to the high estimates for the probability that existence should thrive on other celestial bodies. To try and find a more concrete solution to this enigma, astronomer and astrophysicist Frank Drake proposed the Drake equation in 1961, aiming to quantify the number of alien civilizations that should thrive. The Drake equation calculates the number of civilizations that should thrive by multiplying 7 factors together: the rate of formation of stars in the galaxy, the fraction of those stars with planetary systems, the number of planets per solar system with an environment suitable for organic existence, the fraction of those planets where organic existence actually emerges, the fraction of habitable planets where intelligent existence actually emerges, the fraction of civilizations that reach the technological level where they can dispatch detectable signals, and the length of time those civilizations dispatch their signals. However, the last 4 factors are completely unknown. While we've discovered many planets suitable for organic existence, we have yet to find any actual organic existence. As such, all we can do is speculate about those last 4 factors. Optimists have used the Drake equation to assert that there should be anywhere from 1,000 to 1 million civilizations in the Milky Way galaxy alone, while pessimists have used it to claim that the number of civilizations per galaxy should be less than 1. The mediocrity principle suggests that if an item is chosen at random from a set of objects, the random item is most likely going to be an average example. In this case, the set of objects in celestial bodies that are suitable for existence, and the item randomly chosen is Earth. Logically, our planet should be average amongst all potentially habitable celestial bodies. So why have we detected no signs of existence anywhere in the universe? There are several hypothetical explanations for Fermi's paradox. One is the rare Earth hypothesis, which rejects the mediocrity principle and argues that Earth is uniquely special and that the conditions required for existence to evolve are exceedingly rare. Another proposal is that even if complex existence is extremely common, intelligent existence may not be. Earth has had 5 mass extinction events, and if existence previously existed on other celestial bodies, there's no reason to believe that they could not have been subject to such global catastrophes. Homo sapiens have only existed for about 300,000 years, and the oldest human ancestors were only 2.5 million years ago, which is a relatively short time compared to the 3.7 billion years of existence on Earth, or the 13.8 billion years the universe has existed. It's possible that other intelligent existence has existed in relative proximity to Earth, and we just missed it by a billion years or so. There are a lot of possible explanations for why we haven't detected any intelligent existence, but it's also a numbers game. In the Milky Way galaxy alone, there are anywhere from 300 million to 6 billion Earth-like celestial bodies, and there are as many as 200 billion galaxies in the universe. Even if the odds of existence forming on an Earth-like celestial body were a quadrillionth, that would still mean over 1 billion celestial bodies across the universe should be home to intelligent existence. Our quest to understand the universe is endless, a boundless pursuit that's captivated humanity for centuries. As we venture deeper into the mysteries of the cosmos, each new discovery only serves to lead us further down the rabbit hole of inquiry. So, see ya in the next video. Thanks for watching.